you're building a 9x9 board, standard way.
Yeah, Richard, I
You
can't
can
hear you.
swap entire rows, entire columns, and you can swap yeah, so you can swap segments, and you can swap row and columns in the primary segment. Or you don't really want numbers.
What do you want to talk about it? I think he's talking about it. Yeah.
But you can rotate the board. Yeah. But that's only like that's only 4x more. Yeah. So the idea is you just once you nail down so I guess there's a few ways of doing a brute force search for this.
Yeah.
That makes the thing a little more tricky, I guess.
Yeah.
So basically, there's kind of two orders you can go. You can either swap the row segments. You try so making each one of these there's like six ways of doing it because there's like three things. You just permute them into three ways.
Yeah.
So I guess the first observation is that the order in which you flip these is relevant.
Yeah.
So like it doesn't matter which order you apply these operations. So you just like flip. You first try all the orders and flip the row segments, and then you try all the ordering and flip the column segments. That's 36. That's 36 things you try.
Yeah.
Next thing you try is in the first row segment, first column segment, you do all the flipping.
Mm-hmm.
That I think gets you down. So that's gonna uniquely determine the top left corner, which gives you what exactly which number maps to which. After that point, you just have to flip the next set of rows, like the next row segment, those three rows. You flip them a little bit.
Mm-hmm.
I think that's going to determine a lot of things for you.
I tried all of them.
You tried all that?
I tried all the reciprocal concept. I tried all the implication things.
Oh.
That's probably what I was. I mean, I tried it.
Yeah, basically you want to really take advantage of top left corner.
And it's pretty risky.
Yeah, like basically the thing is like with these problems, it's like as soon as you have part of your state that's kind of like fixed, that's going to give you a lot of pruning power. So somehow that. So I guess the summary of the story is you write a lot of nested for loops, and you prune at some high level, and the rest also prunes fairly easily.
Yeah.
I think Georgia Tech's code is just like a bunch of for loops with a bunch of
yeah, it's kind of same stuff. But I mean, the simulation, I had a lot of mistakes in the simulation, and I misread the problem. So.
Yeah, I think this problem is that you think it's like a Sudoku solver at first, and then it's like anything but a Sudoku solver.
Yeah.
That's what it feels like.
Yeah.
Hi.
I thought I would know myself. I think it's like a legitimate thing to think.
You wanna talk about the next problem then? Problem B. What is problem B?
What's B? I cannot remember.
Oh,
the
you want to talk about it, Artur? So let's have Artur talk about problem B.
Mm-hmm. Yeah, so problem B, I guess everyone read the problem. I don't have to describe the problem.
I will briefly describe it.
It's just you have a huge stack and machine works on the sets instead of numbers, and basically you have to simulate the process. When you push, you create a new set. When you add, you take the two top sets and then add one into another. The problem is like when you simulate, you have to cache the sets, so it will run in time. What you can do is map every possible set to integer, like empty set maps to 0, two empty sets maps to 1, set in set maps to 2, and that way you can do basically like brute force way to like union, intersect, and add. That was our solution. Does it make sense?
Yeah, it's kind of you don't have to actually, because like you don't have like each set is kind of looks like a tree. You don't have to actually construct the whole tree. You just need to know what's the children of the father. You don't have to actually know what's the children of the children, because this kind of tree is defined recursively, and the subtrees you have already defined before, so you don't have to define it again. It's kind of, if you like store the whole tree, for every set you just store the string or you store the hash set or whatever, you will get like too much memories. You will use too much memories, so you have to define recursively. Yeah.
So the sets can get like exponentially large.
Right? Yeah. So that's why you have to define it recursively. You don't have to like, you don't have to. You just need to use some edges to point the relationship between sets. So, yeah. So actually, the largest set can be like 2 to the 2000, right? Yeah.
You guys want to talk about the next problem, problem C?
Hey, anybody want to talk problem C?
So are we talking about it?
Yeah, problem C.
Okay. Yeah, you have some pies that you want to divide amongst you and your friends, and they all have different areas. So it's really easy if you know the size pies you want to divide between your friends to solve the problem. So the idea is basically binary search over that pie size that you want to divide, and then you can greedily just figure out, okay, I'm going to cut this much pie off of each pie. And if you can't do that with all of the pies, then you'll end up getting the wrong, or you'll end up being able to search lower in your binary search, and then otherwise just search higher if you can find a solution with that size pie slice. And then you just print out the binary search value.
Okay, yeah.
Yeah. So let's move on to the next problem, problem D. So the Georgia Tech guys had one solution, and it is very similar to the solution that I'm gonna describe. I guess they were still in the process of trying to optimize it and make it faster, but they just ran out of time. So the basic idea is it's like a minimum Steiner tree, right? You want to add these internal vertices in there, and then you want to connect up all these cities that are given, such that this tree that connects all these cities, including all these other cities, is a minimum Steiner tree, or you could call it a minimum spanning tree. And the key observation in this problem is that you need to construct any Steiner tree. If you're given n leaf nodes, then you need to add this n-2 internal nodes, and you can just brute force that. There are 30 possible vertices, and there are in the worst case scenario you have 8 leaf nodes, so you have to insert 6 internal nodes, and you essentially have 32 6, or it's actually less than that. So you try in a brute force manner, try to insert all these internal nodes, and in addition to that, after you have inserted all these vertices that are going to be in that particular tree, what you essentially do is you want to do a minimum spanning tree in that particular set of vertices to find the minimum cost, and you try that basically for all possible subsets of pairs of 4 cities, and try to add those internal nodes in those cities in a recursive manner. So that was the basic idea for the problem. I actually looked at the judge solution, and I have heavily commented the code, so I'll put it up online, and I'll just email the link to all of you guys so you can just check it out if you want to. But I think the intuitive approach that most of you guys probably had to solve this problem is correct. It was just a matter of of getting the constant down to run it in a good enough in a small enough time frame, you know, like within the specified runtime.
Yeah, and our code is like to find the minimal spanning tree. It's usually using cruise car, but I've built this program in a way like how prime solves the minimal spanning tree, and so my algorithm is something more similar to the prime algorithm for minimal spanning tree. So that's why it runs slower than the cruise car. I think cruise car is like mine code for the largest case is like 6 seconds. I think the solution is like 1.5 seconds. So yeah.
It's actually a little tricky, I think. Like the way the DP state gets done is kind. Wait, Drophead, did E ever come up when you guys were training?
What?
Like, did you see something like E before?
E. You mean E or D?
E.
Oh, are we talking about D or E still?
We're talking about D.
No, we're done.
No,
with,
still
we
not
done.
we're done with D, so we
So
talk about
we
E
talk
now.
about E now. Okay.
Okay.
E is like what's E?
Bookshelves. Was
Oh,
it
I have
bookshelf?
never seen this before, but I haven't seen this before, but actually it's kind of like dynamic programming, right?
Yeah, like the OI like dynamic programming training like up to like 08, 09, that didn't cover this kind of stuff.
Oh, I mean this kind of technique. I have never seen this kind of technique before. Just I thought about that, yeah, in the contest.
A little bit of a weird technique.
Yeah. It's kind of view the problem from another aspect. Yeah.
For problem E.
Yeah, for E.
So do you want to describe the solution?
Okay, what we did is like so. Let me first talk about the brute force way. The brute force way is actually first, for one floor, you will have the maximal height of the books. So you just need to enumerate the rest 2 floors. So you have 7 square time to enumerate the height of the other 2 floors of books. And later on, you can do like snapshots to find the Ys of those books. This will take you like 70 times the total Ys of those books. But we noticed like for each book, its maximal Ys is at most 30. So you will find out like it's very likely like for each floor of books they have like very similar Ys. So you don't actually need the total Ys of 2,100. You will only need like 700 because or a little bit more like 800 or 750 because the maximal Ys is actually at most 30. That's one insight. So in this way you can do in brute force way, but this will definitely run out of time. So one way to improve this is you can basically sort the books. You sort the books from the lowest to the highest. So you start from the lowest, you will realize. So at some time you will say like, okay, I'm gonna never put the books on the first floor again. At this time you will know the height of the first floor because that's the last book you put into because you sort the book from the lowest to the highest. And later on you will never put books onto the first floor again. So basically the state is defined as this. It's like first state is 70 because you have to know which book you are currently dealing with, and the rest 2 states dimension is like 700, which is used for the snapshot and knapsack. Okay, it's for the knapsack, and for the last dimension is like a 3 because you have to see which floor you're gonna never use it again. So it's like if the last dimension is equal to 2, it means like the first floor and the second floor you have is already fulfilled with books. So you're gonna put all the rest books on the 3rd floor. So in this way, the total complexity is like 70 times 700 square times 3. Yeah, and so actually this will make you like memory limit exceeded or some whatever. So for the first dimension, you don't have to make an array of that big. You can ignore the first first dimension, and you use some techniques to use two arrays to shuffle and shuffle and back. Yeah, that's it.
I mean, actually, you don't need to use additional memory. Like if you see the similarity between the knapsack problem, so you can avoid using another dimension. You can just use the existing dimension to calculate it. You can actually see the solution of Jan Cooper, who uses that one.
Oh, okay, yeah. Yeah.
I mean, there are actually a lot of top-order problems where you don't need to use an additional dimension to memory. You can just work on the existing array.
Yeah, I see.
I mean, if you just instead of starting from 0 to total sum, you will just start from total sum to down to 0. So this, I mean, yeah.
Yeah.
So yes, I guess the really weird thing about this problem is like you're doing a sum of mints, but like somehow by sorting the things, you know exactly when like something becomes the mint and like needs to be in your sum.
Yeah.
Just minimize that sum. It's a little strange.
Yeah, actually, I don't see like a similar problem before. It's kind of new problem.
Yeah, it was a little surprising.
It's kind of interesting, yeah.
I mean, we can actually classify this problem as a 2D subset sum. Initially, if we have to, I mean, distribute the distribute the books into two buckets, then it is the standard subset sum problem or standard knapsack.
Well, the issue is how to track the height.
Yeah?
The issue is how to track the height. Like that's the funny part. About
Yeah.
it. Like
Yeah, but
there's a height multiplied in.
yeah, but you need to actually minimize the height, so which is actually quite common pattern in DP.
Well, but like, how do you know like when something becomes the min? Like usually, like the standard DBC that comes to mind is like here are the min height of all my times, separating into states. That's kind of like
Not
the
in height. You need to minimize the sum of the heights.
right.
Sum
Well,
of the
the problem is the height
heights
is not max. It's not like summing over everybody.
Yeah. It's kind of why why I got this intuition is like because if you don't like store height in your array, it's you actually will make a Boolean array, but it's kind of when you are doing dynamic programming, if you use a Boolean array, it's kind of wasting actually. You must store some integers in the dynamic programming array so that you can actually make your process more efficient. I don't know. This is kind of weird stuff. I'm not sure if it's kind of intuition. Yeah. Yeah.
Okay, the next problem then, problem F. See you on Thursday.
So we're going through F now.
Yeah.
Let's see. Wait, who's going?
Printer queue. Okay.
Wait, we're doing problem goes by.
Problem F, printer queue. Did you do problem?
Oh,
I think so.
you want to talk about it?
Context problem. Oh.
Have jobs and
Oh, it's hard to hear.
you have a queue of printing jobs and you take the first one and if it's not the max then you just put it at the end and if it is you print it out. And so you can just simulate it to find when you will have the job that you want printed out. It's not really okay.
Pretty straightforward.
And it's a high power use case.
No, we just
Probably move on to problem G then.
so
It's asking for the shortest path in this unweighted graph on like 9,000 vertices for the 4-digit prime numbers. So you can just construct the graph and invest. That's it.
View those straightforward. So the next one, I guess, a pretty interesting one, H. So do you have some ideas, guys, for H?
I can talk about H because I actually just solved it after the contest. I was missing one corner case. So this is kind of an irritating problem. So they describe this landscape to you, and a couple important things is that there's only 500 points that are defining the landscape, and that all the coordinates that they're defining it with are integer. So what that lets you do, and also that the xi are strictly ascending. So those are the important things. So what that means is, because they're on the integers, between, so you pick some starting point for your interval that you're going to take. And then you go L away from that, and that's going to have some value. And if you do a ternary search on that, and if you were to place it one forward, a ternary search over that 1 unit range, you're going to find that you're going to be able to, it's either going to have a minimum somewhere in between or on the edges. So you can actually extend that idea and only look at certain critical points, which are either when your left side of your interval or your right side of your interval are hitting a new vertex on this landscape. So through a lot of careful coding, you can actually solve this with a lot of ternary searches.
Well, your ternary search eval function, you can just code that in like order and time, right?
That's right. Yeah.
So you put the eval function in order and time, and then just ternary search on each interval.
So it's not on each interval.
Well, so like you have a bunch of key points where things break down,
Yeah.
which are specified by the x values. So like say like my ternary search function just wants to do eval for like a single location, which is like my x coordinate, some x coordinate. I claim that like the only time where the function is not like convex is when x hits one of these peaks, or like x plus h hits one of these peaks. So all you do is you just take all the x values of the peaks. You take all the x value minus h, well, minus the width of your airport. You take all those values, sort, ternary search on each interval. That actually removes most of the special cases, I think.
Yeah, the only special case that I'm not sure if that handles, and that's what made me do this complicated solution, is consider if your optimal place to cut is just the top of the mountain. So like a triangle, you may not actually cut on an integer, and it may be optimal just to like cut around this triangle.
Yeah, but then the peak minus h and like the peak, that point is in that region. I'm gonna actually hit that with my ternary search. Like that's one of my events in my ternary search.
So your events are...
My events are all the x and all the x minus w. Well, is that w or is that what's the width? Oh, L. So it's all the x and all the x minus L. I take all those values, I sort them.
Okay, yeah, that's the same thing.
And then I just ternary search on each one of those consecutive points.
Yeah.
Do we even need ternary search? Like maybe some people hill climbing will work as well. Like I guess the bounciness problem is small enough that like if you just like hill climb on enough points, you're gonna find it. Some funny sense, I guess.
Could be. You just might have problems with precision.
Yeah, the next one, problem I.
I can talk about it.
Yeah.
So you essentially have this permutation, and what you're trying to figure out is if this permutation is a perfect square, is what the term is. And there's actually a rule that follows that you can prove to yourself pretty intuitively by just doing out a couple test cases, which is that if a permutation is a perfect square, then that means that any the frequency of all the even cycles, or the frequency of cycles of even length. So like the number of 4 cycles I have, that has to be an even number. And that's true for all even cycle lengths. The odd cycles actually don't matter. So you just decompose this into its cycles and then figure out the frequency of each cycle.
Some way to know that that's the characterization of spread permutations. Prove it. Why?
I don't actually remember the formal proof, but if you just do have a couple test cases, you can see that if you had some odd permutation, then you can just apply it again and it stays odd. Yeah.
So the proof is like, if I'm not I look at the cycle structure. Then like you have cycle structure. Well, but the thing is, so you need to prove 2 things. You need to prove that this kind of structure. Like basically, so you want to prove sufficiency. Yes, we proved one direction. So if it has the structure, then it's oh, but then like then the other direction is like you take a permutation, you look at the cycle structure. Yes. And you claim that like once you square it, you look at what happens when you square a cycle. Because when you square a permutation, you're just like moving 2 steps along a cycle. So that gives you the cycle structure. So you're saying the cycle either divides in half or yeah. Basically. And that basically is like even length cycles become 2 cycles, and odd length cycles just stays the same. So at that point, well, they advance by 1, but you're kind of just like hopping around down them, and that basically proves your necessity. Yeah.
Cool.
So what's the plan for next weekend?
So it's NWERC 2011. So University of Calgary is gonna host it. Darko.
There's that like New York party now.
Huh?
But there's like that like party in New York about like somebody. I think Sean just posted a link about like a New York.
Oh, the Spotify thing. What day is that?
Saturday 2 p.m.
But it is in actually February 18 maybe.
Oh, it's not next week. Okay. Plus next week on Saturday there's Hacker Cup at 4, right?
Yeah, 4 p.m.
4 p.m. Eastern Standard Time. So it'll probably be Sunday then next week, right? The practice. And it seems
So
like
we are good with Saturday or Sunday.
yeah, probably Sunday next week.
Okay.
Okay, see you guys for this.
Sorry.
Oh. So yeah, it's probably gonna be Sunday then, right? Next week.
So you have Hacker Cup participants, right?
No, none of the guys are doing it. Are you guys doing it?
I'm not sure.
Did you compete
It's the
yesterday?
first thing they
Stanford coach is the only one who's left in.
Maybe one of the guys is doing it. The other guys just forgot about it.
Okay.
I think like J-Lo is the only one who's in there now. Oh, and the Michigan coach, like the Stanford and Michigan coaches are in there.
Okay.
And that's about it. But for them, like it doesn't really matter, right?
Yeah.
So if there is no participants, actually we can compete on Saturday.
Yeah, we should probably email tomorrow and
Yeah,
see.
yeah.
Yeah.
Yeah, let's see.
Okay.
That's one of the
Okay,
like,
guys.
go one.
Yeah.
See you.
See you.